Hey, let's review kinematics. So I assumed you guys already copied down this little chart right over here. It's very helpful at remembering how we interpret number lines. And we're gonna hop right into the topic as a whole. Okay, so when we're thinking about kinematics, we're thinking about linear motion. We're thinking about motion along a line. So if you wanted to think about the origin as the starting point, right? And any motion to the right of the origin would look like this. Any motion to the left of the origin would look like this. If you took this motion and kind of rotated it and superimposed it onto the XY coordinate plane, it would look just like this, where motion to the right is above the x-axis, motion to the left is below the x-axis, and then on this particular one, we end up kind of right back at the origin where we started. So this is what that linear motion graphed on the XY coordinate plane would look like. That's what kinematics is. It's graphing this particle's motion over time. So the way that we use kinematics in derivatives is we have an original function thought of as the position function. Then we have the velocity function. The way we get from the position function to the velocity function is by taking the derivative, which makes perfect sense now because the velocity tells us the speed at which the original particle is moving, and then if we find the derivative of that, it tells us basically the speed of the speed or the rate of the rate, which is what the second derivative is. So this guy is the acceleration. And the way we get from the velocity to the acceleration is by taking the derivative once more. So this is a summary of the position function and what it means. And I'm going to drop that right down over here, okay. So that's going to be kind of an explanation of the position function. Now, the velocity function can tell us some important stuff as well. When the velocity function is set equal to 0, this indicates that the particle is changing direction or just momentarily at rest. Both things. Changing direction momentarily at rest. Okay. Then we have the acceleration function. And if we ever get the acceleration function set equal to 0, that's going to tell us that the velocity of the object is currently constant. Constant or unchanging. Okay. And if you ever want to contextualize what's happening with the position, velocity, and acceleration function, I'd try using the moving man because I feel like he really kind of puts everything all together for you. He's a good visual. Okay. So whenever we have the position, velocity, and acceleration functions, we can create number lines for velocity and acceleration. We can kind of line them up, and that will help us determine whether the particle is speeding up or slowing down. It'll also help us describe the motion of the particle, if that's what the question is asking us to do, right? So if we take some position function, find its derivative, and create a velocity number line of it. Oh, why is this moving everything I write? Hang on. Maybe it'll go away if I stop touching it for a second. Okay, and we found that the two values where it stopped moving. Great. The two values where v of t is equal to 0 occurred when time equals 2 and time equals 5. Let's say we tested values a little below, one in between, and one above in order to generate the signs along this velocity number line. And we got a positive, or sorry, let's do a negative, a positive, and a negative. Then we took the derivative of the velocity function, found the acceleration function, created a number line of that guy, put it right below, and lined it up. And we found that guy to be 0 when t equals 3. Then we tested a little below and a little above. We got a negative here and a positive here. I just want to go over how we would interpret these two number lines stacked, because I feel like we're pretty good at making number lines, right? So if I were to interpret this particle's motion, right, I would know that this guy is speeding up when the velocity and the acceleration have the same sign. So this guy is going to be speeding up from 3 to 5, and then again from 0 to 2. So we would say that this guy is speeding up from 0 to 2, and then again from 3 to 5. Let's say this guy starts at 0. And the reason why is because velocity and acceleration have the same sign. Whereas this particle is slowing down when velocity and acceleration have different signs. So when we have something that looks like this, between 2 and 3, we have different signs. And then from 5 onward, we have different signs. So we would say this particle is slowing down from 2 to 3, and then again from 5 onward. Okay, so that's pretty much all you need to know. I guess something I would also mention, just 2 little one-offs. Displacement is not equal to total distance traveled. Remember when we told that Mad Lib story? We lived a whole life from origin to return to the origin, right? The total distance traveled is not equal to the displacement. The displacement is when you evaluate S of t at a particular t. That'll tell you that particle's distance from the origin at that time, whereas total distance traveled is all the loops and turns that it's taken until it got to a certain time. Another thing that I wanted to mention is, if you think about the graph of position, right? And you wanted to find the particle's maximum distance from the origin, it could be in the right or left direction. So you could be finding a max or a min of that graph, and you would just have to make a call on which one has the highest magnitude. All right, let's do a kinematics problem together. We're going to scroll down to question number 8. I lied. Question number 11. Someone just goes, oh, okay. So, a particle moves in a horizontal line so that its position from a fixed point after t seconds, where t is greater than 0, is s meters, where s of t is equal to 5t squared minus t to the 4th. Find the position, velocity, and acceleration of the particle after 1 second. So I graphed this guy over on my calculator just to save some time for the video. You can pause the video and graph it at home if you want. It says that I'm going to need to evaluate the original for 1, the velocity function for 1, and the acceleration function for 1. I'm going to go ahead and add a calculator. I have my position function stored in F1. It says that the calculator is okay for this question, just so you know. So I'm going to evaluate F1 of 1, and I'll get my answer. I'm going to do numerical derivative at a point, menu for 1. The value here is 1, and I'm going to evaluate the first derivative of F1. This guy is 6. I'm going to do the same thing, but now I'm going to find the second derivative because I need to find the acceleration when time is 1. Menu for 1. This time, however, I'm going to change first derivative to second derivative. Still using F1. And my answer is -2. So let's just tack on the appropriate units. So 4 is going to be 4 meters to the right of the origin. 6 will be 6 meters per second. And -2 will be -2 meters per second squared. That is us evaluating all of those things very quickly. Yay! Letter B says, find the values of t when the particle is at rest. So a particle is at rest. Oh, I'm so sorry, I skipped B. Determine whether the particle is speeding up or slowing down at time equals 1. So we are going to need to set up some little number lines to answer this, or we can kind of look up at what we have set up here. You could totally set up number lines if you wanted, if this was a test and you just wanted to be perfectly sure. But let's try to do this quickly, right? If velocity and acceleration have the same sign, the particle is doing what? Speeding up. If velocity and acceleration have different signs, the particle is doing what? Slowing down. Since they told us at time t equals 1, didn't we just find the sign of the acceleration and the velocity when time equals 1? We did, and they happen to be different. So we're going to say the sign of velocity and acceleration are different at time equals 1. Therefore, the particle is slowing down. Okay, now letter C says, find the values of t when the particle is at rest. A particle is at rest when v of t equals 0. V of t equals 0 is when a particle is at rest. So let's try to think of a fast way to do this. You could what? Yeah, you could find the root. You could find the derivative and then find the roots. Absolutely, set it equal to 0. Yeah, let's do that. I feel like we've been doing a lot of calculator work. If you wanted to do it quick, you could also just graph the derivative here and find where this original guy crosses the x-axis. Right? So you could either do it by hand or you could do it on here. It looks like the particle is at rest when time is equal to 1.58 seconds. And you could just draw a little sketch, right? You had your original. This was s of t. And then you have your derivative. He's just steeper, kind of doing the same thing though. This is v of t. His 0 is at 1.58 comma 0. Okay, so this would be enough work to demonstrate. Then on D, it says find the time. I did it by hand on the answer key too, so if you want to see like the long way with the math, you can look on there. But D says find the time intervals on which the particle is speeding up and the intervals on which it is slowing down. So we have our graph of the first derivative, right? Let's interpret that guy and make a number line, huh? It's starting at 0. This is the velocity number line. The outputs of velocity are positive, meaning above the x-axis, until we get to 1.58, which is a 0. And then to the right of 1.58, all the outputs of the derivative are negative. Since we're already working with the graph of the derivative, why don't we do the same thing and kind of cheat with the acceleration and save some time, right? Let's graph the second derivative of f1. Sometimes it gives me trouble when I try to graph the derivative of a derivative graph. So I'm just finding the second derivative of the original just to avoid that issue. It doesn't always work, and I just don't want to deal with it, so. All right, this is the derivative. I think I'm going to add a few more y's just to see what this thing looks like at the top. All right. This is the second derivative graph, and I'm going to find the 0 of this guy so I can make my number line. So the 0 of the second derivative number line is going to be 0.913. Okay, so to the left of 0.913, we have positive outputs on our second derivative graph. To the right of 0.913, we have negative outputs. So we can go ahead and line this guy up, and we have the same sign from here to here. And then again from here to here. Then we have different signs from here to here. So let's go ahead and try to write these time intervals, okay? So we are speeding up when t is an element of all reals, such that we are between 0 and 0.913. That is when we are slowing down. Instead of rewriting that, I'm just going to write slowing down. And then we are speeding up for the green. We are speeding up from 0 to, wait, what did I do when I'm writing this? Oh my gosh, let's just set this up. Okay. Slowing down from 0.913 to 1.58. Then we are speeding up from 0 to 0.913, and then again from 1.58 onward. So let's just write t is greater than 1.58. All right. Okay. Find the total distance the particle travels in the first 3 seconds. So total distance traveled is going to come from the position function. So I'm going to go back to my graphs. I'm going to delete the derivative because there's a lot of noise going on this graph here. And I'm going to get back to the original. Okay, so I have just my original, right? And I'm going to adjust my window so I can just see what's going on from 0 to 3. I'm going to give myself a little margin here, okay? And then I'm going to go back in here and I'm going to cut off the graph from 0 to 3. Okay, so it looks like I need to add some more negative numbers down here. Okay, cool. So now I've got an image of exactly what this thing looks like from 0 to 3. I'm going to find the total distance traveled to get to the farthest point right, which is going to be the little maximum of this thing. And then I'm going to find the total distance traveled to get all the way down to this guy, okay? So I would be traveling 6.25 to get up to the top, 6.25 to get back down, and then 36 to get to the very, very bottom. And I'm just going to do my little sketch here so I can show what's going on here. That's not at all in proportion. Hold on, let's do. There we go. Okay. All right, so I would add those all together and I would get 48.5. Okay, so that's kind of everything for kinematics. Bye.